Okay. Can everyone hear me? We good? Okay.
Yes.
Works for me.
Okay. Nice.
Yes, sir.
Today we're going to cover the section which deals with the completeness property of the real number line. We won't know what that is until the very end of the lecture, but that's where we're going. And we're going to begin with the following definition. So, definition 2.3.1. And again, the way that I write the definitions is sometimes different than how the textbook writes them. So, we're going to let S be a non-empty subset.
Your
Professor, you're
camera has
unfocused.
like completely unfocused. It's better.
So let S be a non-empty subset of R, okay? And just let me know if it blurs out again. So for A, we say that S is bounded from above
It's doing it again.
Let me see if I turn on this light here. That'll help adjust the balance. Okay. So, all right. So we say that this non-empty subset is bounded from above if there is a real number say, I don't know, X, so that little s is at most X for all little s in set S. Okay? So this is what it means for a set to be bounded from above, and similarly, B, S is bounded from below.
Oh, it's blurry as hell.
I don't know why it's doing that today. Let me adjust my video settings. Okay. So I'm just going to have to keep my eye on the camera now. So S is bounded from below. If there is a real number y, maybe, so that y is less than or equal to little s for all little s in the set capital S. Okay. So this is the notion of being bounded, and if S has at least one of these bounds, we say this bounded from above or below, but we only say the set is bounded if it has both a upper bound and a lower bound. So I'll just go ahead and write that. So we say S is bounded if S has a upper bound and a lower bound. Okay, so only when the set has both of these do we say that it's bounded. Okay. So, for example, maybe we could look at the set S, which we define to be the set of all x in real numbers, so that x is less than 2. Okay. So on the real number line, what does this look like? So here's a 0, 1, 2. So all of this over here. So all of that, that's going to be S. So in this case, we say that, okay, we can obviously see when we draw a picture that S is bounded above by 2, and S has no lower bound. There's no lower bound that we could ever find that would bound every element in that set. So S is bounded from above, but we would not say that S is a bounded set. Okay. Now, one thing to observe is that, for example, here we have an upper bound, 2, but if we have an upper bound, we have an infinite number of upper bounds. So if there is one upper bound, and this could likewise be said for lower bounds. So if there is one upper bound for S, then there are infinite upper bounds for S. And likewise for lower bounds. Right, so for example, 2 is the upper bound on this set S, but also 3 is an upper bound for this set S, 2.5 is an upper bound for this set S, 4 is an upper bound for this set S, so forth and so on. Okay. So this is an example of an unbounded set. Now I'm going to draw a set that's bounded both from above and below. So we have this R, and then the set could be something like maybe that, maybe some stuff there, maybe some stuff there, and maybe some stuff there. So that in green there, and if you can make out that if that's green, but that's S, okay? So now this set here, this is bounded from above and below, so we would say that set is bounded, okay? Now, when considering bounded sets, we're going to want to somehow consider the boundaries of that set, right? The numbers that are as close we can get to S from below and from above. And that leads me to the following definition. So I don't know the number for this definition, I'm just going to write it out.
Excuse me, sir. It's not clear. I cannot read the board clearly. I don't know, maybe the camera. It's not clear. Everything on the board for me.
So on what part is it not looking good right now?
I mean,
Okay, so recording again, I'm going to write down this definition that is going to be concerned with the smallest and the biggest bounds on a bounded set. So let's say, okay, part A, I guess. The supremum, so the supremum of a set S, which is bounded above. In order to have a supremum, the set has to be bounded above. So the set S, I'll go ahead and write that down. That is bounded above and this is written sup S is the least upper bound for S. This is the supremum. It's the least upper bound. So for example here, whatever that number is right there, that would be sup S. Okay. So part B, the infimum of a set S that is bounded below and this is written inf S is the greatest lower bound. Okay, so that's the infimum. The greatest lower bound, the largest lower bound out of all possible lower bounds. So here, this would be the infimum. Okay. So one way to define these with inequalities instead of just with words would be, so let's go ahead and do that. So this is like a continuation of that definition over there. So I'll say U is equal to sup S. So it's equivalent to saying, it's like if and only if V is an upper bound for S, then U is less than or equal to V. So saying something is the supremum of a set is saying that If you pick any other upper bound of that set, then that upper bound is greater than or equal to the supremum. If U is the infimum of S, that's equivalent to saying if V is a lower bound of S, then so V is less than or equal to U. So this is describing it with words, and that's describing it with like an inequality that you can like test. Okay. So, for example, let's look at a test set here. Maybe S is equal to the set of all real numbers R, such that 1 is less than or equal to X, which is strictly less than 2. Okay, so what would be the infimum of this set here? So this is clearly bounded, right? It's bounded both above and below. So for example, 0 is a lower bound on S, right? 0 is a lower bound on S. But is that the greatest lower bound?
No.
Right. For example, 1/2 is also a lower bound on S. But is that the greatest? No. You keep on going further and further, you'll see that 1 is the infimum. So what's the supremum of S?
2.
2.
What? Say that again?
2.
2. Among all possible upper bounds, this would be the smallest. Now I want you to observe now that in this case here, the infimum does belong to S. However, the supremum does not belong. So it can be the case that the infimum and supremum are contained in the set, but they don't necessarily have to be. They just have to be the closest number you can get without entering the set, if it's not in there. So it should be clear, by the way, that with these definitions that for a given set S, both the supremum and the infimum are unique. Okay, you can't have more than one supremum. If you assume that there's more than one, then you get a contradiction that one of the two numbers you assume to be the supremum wasn't the largest. Okay, so just make some more room. Does that make sense though while I'm drawing this off? That there cannot be more than one supremum or infimum?
That makes sense, but for like a point, could the infimum and supremum be the same?
Yes. Good question, by the way. I definitely should have mentioned that. And that's an example of one of these odd sets that satisfies a very strange property. In fact, a set consisting of one point is the only set that will have that property. So, Okay, but in general, sets will satisfy one of the following conditions. So we have, so both infimum of S and the supremum of S exist. And we will learn at the end of class, or state, that every bounded set has both the supremum and the infimum. The other possibility has an infimum, but no supremum. So that would be the case if you have a set that's bounded from below. Another possibility would be has a supremum but doesn't have an infimum. So this would be a case where the set is bounded from above but not from below. And then finally, no supremum or infimum. So every subset of the real number line is going to satisfy one of these, exactly one of these. So let's draw another picture and see if we can get a formal and visual or geometric representation of supremums and infimums. So let's suppose our set maybe looks like this. So this is our set S. Okay? And maybe it doesn't contain its supremum. We just know that its supremum is right here. So S, and I'll say that's equal to U. There's some number right there, call it U, that is the supremum of the set. Now, if that's the supremum of the set, then there is no number that bounds S from above that's smaller than U. So what does that mean? It means that if I subtract off anything from U, it's no longer going to be a upper bound, right? It's the smallest upper bound. So if I subtract anything from it, it will no longer be an upper bound for S, which means there has to be an element in S that's larger than it if it's no longer an upper bound. So if this is the case, so if U is equal to sup S and epsilon is any positive number, real number, then U minus S is not a upper bound for S. Or no, U minus epsilon, I'm sorry. U minus epsilon is not an upper bound for S. Is that clear? If that's the smallest upper bound, right? If I subtract off anything from it, then it's no longer an upper bound, which means that, what does that mean about S? It means that S contains something larger than U minus epsilon. Just looking at this picture here, if I move anywhere this way from U, anywhere, I'm going to go into the set S. Okay? And you can imagine an analogous for the infimum. If I add any positive number to the infimum, I'm no longer a lower bound, which means that there's going to be an element in S bigger than infimum plus epsilon. Okay. By the way, is that notion clear? This epsilon notion. I didn't hear anyone speak up when I was talking about it, but it's a really important concept. So y'all can talk. Does that make sense? If not, I can walk you through the reasoning for it.
Yeah, it makes sense because if epsilon is bigger than 0, then your u gets dragged down below what your supremum is, so it wouldn't be your supremum anymore.
Right, so it's just important to remember that, so if epsilon is a positive number, then u minus epsilon is less than u. Right, if that's the supremum, just remember that u is the supremum. If you subtract off a positive number from u, then you make a smaller number, right? So if that were to be the case that this was an upper bound on S, then that wasn't your smallest upper bound on S. Which means that that can't be an upper bound on S. So that means there's something in S that's larger than that. So, for example, yeah, well, let's say it. So if u is equal to the supremum of S, and epsilon is greater than 0, then there exists some element S that's contained in capital S, so S sub epsilon, so that u minus epsilon is less than S epsilon. That's what this implies. So this statement about subtracting off a positive number from the supremum not being an upper bound for S implies that there is some number in S that's greater than u minus epsilon. That's what that implies. Okay. Does that make sense? I don't want to move too fast, and I definitely want to hear feedback from at least some of you. Any comments on that notion? It's a really important notion before we move forward. All right. So let's move forward. Okay, so we're going to move forward by proving a lemma that will be useful. Oh, well, actually, we'll be proving this, but a stronger statement than that. So this is 2.3.4, it's a lemma. So lemma. It states that u is equal to the supremum of S if and only if epsilon greater than 0, there exists some element S sub epsilon contained in S, so that U minus epsilon is at most S epsilon. So it's a biconditional statement, stronger than this statement here. Not stronger, but it's the more general version of it. So let's look at the proof of this. So we have two directions to proof. Okay. Now, when I moved my camera earlier, I kind of excluded that little piece there. Okay. So there's two things to prove here. We have to prove if U is the supremum, then for every epsilon stuff, but then we also have to prove if for every epsilon there exists this element, then U was the supremum. Okay. So how can we do this? So maybe we'll just like write out because this is almost the proof of one of the directions of this biconditional statement. So maybe we can just write out first, suppose U is the supremum of S. Okay. And let epsilon be greater than 0. Okay. Then, since U minus epsilon is less than U, it must be the case that that number, so that U minus epsilon is not a lower bound for S. Oh no, not lower bound, upper bound. Upper bound for S. And the reason for that is U is the smallest upper bound for S. So any number smaller than that can no longer be an upper bound for S. Now, since U minus epsilon is not an upper bound for S, then S has at least one element that's larger than it. So we can say, therefore, maybe S has at least one element I'm going to call it S sub epsilon with U minus epsilon strictly less than S sub epsilon. So that proves one of the directions here, if that, then that. So now we have to prove the converse. So conversely, suppose that for every epsilon, there is some element in S so that U minus epsilon is less than element. There exists, sorry. So S sub epsilon contained in big S, so that U minus epsilon is less than S sub epsilon. Now, so we want to show that U is a supremum, which means what? We want to show that any upper bound for the set S must be greater than or equal to U, because U is the least upper bound for S, right? So that's what we want to show. How can we do that? Somebody, I need y'all to start talking more with me. Anybody? We're just working with definitions right now. There's nothing fancy that we're doing. It's just, we assume a definition, which we have the Supremum definition, and that definition implies just through proof techniques, like the basic ones. We're not doing we don't have any heavy machinery. We just have one definition. We want to show that it satisfies that definition. If this happens, why does that definition satisfy? Why is it satisfied? I need at least one of you to speak up. At least tell me like what proof technique would be your first instinct. You have direct proof, contrapositive, contradiction. Of those
Direct proof?
So direct proof is one way. So why? So I'm just curious why you said direct proof out loud.
Because it's basically exactly what you told us the theorem was, or am I wrong?
No, I'm not saying you're wrong at all. I'm just trying to see the easiest way to do a direct proof. That wasn't my initial thought, so let me think.
Or a proof by contradiction, would that be better?
I think that's the quickest way for me, but
Okay.
it might be doable directly. So, yeah, it might be provable directly, but let's do contradiction just for the sake of time.
Okay.
So notice over here I drew U.
Yes.
So then I'm going to suppose that U is not the least upper bound.
Okay.
Right, that's the contradiction part. So if it's not the least upper bound, then what? Then there's some V that is the least upper bound,
Yes.
right? So what does that mean? That means that everything in S is contained over there, right? And again, I mentioned this last class, when dealing with analysis proofs, it's a good idea to start drawing the real number line to get a sense of what's going on. Okay. So U satisfies that property, and by contradiction, we assume that it's not the supremum, which means there's some upper bound on S that's smaller than U.
Yeah.
What's the problem?
What was the question?
So why is this picture implying a problem about what we assumed? So U satisfies this. Right, so U satisfies that.
Yes.
And we assume by way of contradiction that it's not the supremum, which means that we get this B, right? Assuming it's not the supremum means there is a smaller upper bound on the set S, right? So look back at what we assume, and then look at this picture. Why is that a problem?
There are epsilons between V and U that don't.
You're so very close.
Okay.
Not epsilons. Well, when you say epsilons, what do you mean?
I mean values that you could subtract from U that don't make you fall into V.
They don't give you an element from S.
Yeah, that. Sorry.
But if I like expand it out a little bit and like zoom in, and like U is like here, then right there would be like U minus epsilon, right? But notice with the picture, there's nothing from S that was over there, right? If there were something in S, it was contained there, like here. If that was like S epsilon, then V would no longer be an upper bound, which means that V couldn't have been the supremum. So to make this precise, maybe, what we can do is just say, if there's separation between V and U, I can just say, take the distance from V to U and just divide it by 2 and set that equal to epsilon. That way we go halfway between them. Is that making sense?
Mm-hmm.
So I'm going to say, so by way of contradiction, suppose that U is not equal the supremum of S. Okay? Which means that there is a smaller upper bound on the set S. And we're assuming, by the way, I didn't write it because I didn't have room, but we're assuming that S is bounded from above. So there is some bound. So by way of contradiction, suppose U is not the supremum, then there is a upper bound of S, maybe call it, say, V, with V less than U, strictly less than U. Okay? So in this case, where that happens, we can just set epsilon less than U minus V. That's less than the distance between them, right? In this case, let 0 be less than epsilon, which is less than U minus V. So epsilon is just not halfway between them. It's just like any number that's between them. Any distance that's not exactly V to U. Okay? Then there exists, by our assumption, there exists some S epsilon in S with U minus epsilon less than S epsilon. Okay? But if you rearrange this inequality right here, if you add V to both sides and subtract epsilon from both sides, you get what? You get that V is strictly less than U minus epsilon, right? Subtract epsilon on both sides and add V on both sides. Okay? So hence, maybe V is strictly less than U minus epsilon, which is strictly less than S sub epsilon, a contradiction because V should have been an upper bound for S. You see how it worked out like perfectly there? If V was less than U, then if I pick epsilon less than U minus V, then we get immediately that V could not be an upper bound because it's less than that thing, and that's an S. That's the contradiction. Okay, so I probably should have said before I wrote this lemma that let S be bounded from above. So that's important to put in your notes. So let S be bounded. That'll work as well. Bounded from above. Okay. How much time do we have? A little time. So, okay. Let's go ahead and write out now the completeness property of arc. So we don't have the tools to prove this property, but it's important that we note it because it's going to be used in many of our subsequent arguments in sections that we're going to cover. Okay, and this says every non-empty subset of the real number line, not the real number line, the real numbers, so every non-empty subset of R that has an upper bound has a supremum. And this is going to be used a lot. So in your notes, put like a big star by this. Now, assuming this property, you also get that every non-empty subset of R that is bounded from below has a infimum. You can take this and translate it to infimum by just considering an infimum, a set that's bounded from below, multiply everything by negative. By this property, it's bounded above, which means the original one had an infimum. So this is important. Okay. All right. So that'll be it for the recording of today's lecture.